Hello and welcome to this video. In this video you will learn how the Marsaglia generator works. This is a method of generating standard normal random variables or even any kind of normal random variables. In this video I will make some references to my Box-Muller video, so I suggest you watch that first. This method is in some ways better than the Box-Muller method because this method avoids the so-called trigonometrics functions. I will start by going through the theory, and then I will implement an example in Python so you can see that this algorithm works. Now, if you enjoyed the video, please give it a like and subscribe. And well, then just please enjoy this video. Okay, now I'm ready to go through the theory. So our goal is to simulate x from a standard normal. The algorithm which we will use to do this is this Marsaglia algorithm. Here we sample u1, u2 from a standard, no, sorry, not a standard, but from a uniform -1.1, and they are independent and identically distributed until u1 squared plus u2 squared is less than or equal to 1, and we call this r squared. Then we return a set equal to u1 times the square root of 2 times the logarithm of r squared divided by r squared. Then my claim is, and this is what I want to prove, that Z has the same distribution as X. So that is, Z should be standard normal distributed. And this is far from clear, and this is going to be a long video because there's a lot of theory going into proving this. But finally, in the end, I will go through a Python example where I show that it works in practice. So let's go down here, if it will let me. It won't. Okay, fine. So let's consider a pair u1, u2, where we sample them as above. If we draw a coordinate system, that means we have -1 here, we have 1, I think this is going to be a bit uneven, let's put it here, 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 1, -1, then our u pairs will lie within this box. So somewhere in here our u1, u2 will lie. We then keep trying until r squared, which is equal to 1 squared plus u2 squared, is less than or equal to 1. This is the same as r being less than or equal to 1, and r is exactly how we find the radius. This is the radius of the distance from origo to this pair. So we throw away all points which fall outside of the unit disk. This disk has radius 1, and we throw away the pairs where this radius is greater than 1. Now, if we consider some point, if we say this is our point, u1, point u2, let me just put the arrow up here, then instead of writing the coordinate as one coordinate and the other, we can use polar coordinates. So we can write it as the distance and the angle. So this is the radius and this is the angle. Then u1, point u2 can be written as the cosine of theta, the sine of theta, and then both multiplied by r. Okay, we have established that our u1, u2s are identically distributed within the unit square. That means that the distribution u1, u2 taken in some u1 and u2 will be equal to 1 divided by the area of the unit square, but that is just pi. Now I want to somehow find the density of theta and r, and we know these can be written. We know there's a function f1 which takes u1 over into the cosine theta multiplied by r. I should probably write the r on the other side, and an f2 taken u2 over into r sine theta. So the way we find this distribution is that we take the distribution of u1, u2, and then we multiply it by the determinant of the Jacobian matrix, where the Jacobian matrix is the matrix where I think this is going to be a bit too small, like this, df1 d theta df1 dr. So we take the derivative with regards to one variable, then the other, and then we do this same for the other function. So this function is r times the cosine of theta, so this will be equal to r times minus sine theta. Down here we will have just cosine of theta. Up here we have r times the derivative of sine theta, which is cosine theta. And down here we have sine theta. So we get that this, the determinant, will be equal to minus sine theta squared. No, wait a second. So we take this entrance multiplied by this one, that is r sine theta squared. And if I then subtract this entrance with this one, we can take the r outside, and then we have cosine theta squared. Let me just move the squared in here. Okay, so when we take the numerical value, we just get that this minus disappears and this becomes a plus. Then it's a well-known result that this is equal to 1. I will not prove that. So we get that this is equal to r. So if we go up here, we can write this as 1 over pi multiplied by r. Now we can write this in a different way. We can write this as 1 over 2 pi multiplied by 2r. Nothing has changed. Then we can say that this is the density of theta, and this is the density of r. Then we have that theta and r are independent, since their joint density can split up into a product of their marginal densities. Okay, this is very important that theta and r are independent. Now I continue. I claim now that r has the same distribution as the square root of a uniform distribution. To consider this, consider the square root of u being less than or equal to some r. That is equal to the probability of u being less than or equal to some r squared. I was using small r this time. R squared, which, since this is standard uniform, simply, at least for r in 0 to 1, this will be equal to r squared. Now, this is the CDF of u, or this is the CDF of square root u taken in r. So to get the density f square root u of r, we have to take the derivative with regards to r, which will then be 2 times r. But this is exactly, if we instead had written large r here, this would exactly be equal to the density of large r taken in r. Because we found up here that this density was 2 times r. I should have used a small r here. So this is correct. Okay, now I claim that u1 squared, our coordinate pair, plus u2 squared is also uniformly distributed. Where this is a standard uniform. And that this is independent of theta. Well, consider u1 squared plus u2 squared. This is equal to r squared. This is equal to r squared multiplied by the cosine of cosine squared of theta plus the sine squared of theta. But this is equal to 1. So this is equal to the radius squared. But the radius squared has the same distribution as some uniform, or r has the same distribution as the square root of some uniform. So this squared has the same distribution as a uniform. So this is fine. Also, we know that r is independent of theta, which means that a function taken on r will still be independent of theta. So this claim is also correct. Now I claim one more thing. I claim that E1, a standard exponential, has the same distribution as minus the logarithm of u, which then has the same distribution as minus log r squared. Now, if we consider the probability of minus the logarithm of u being less than or equal to some x, then this is equal to the probability if we multiply by 1 over minus 1 on both sides, then we get that the inequality turns around, and then we take the exponential on both sides. So we get that u must be larger than or equal to the exponential function of minus x. This is the tail function of a uniform. So this is equal to 1 minus this guy. But this is exactly the CDF of a standard exponential taken in x. So this is also all right. Now, finally, we have that a pair x1, x2, where x1 and x2 are IID, normal, 0, 1. This, I argued in the Box-Muller algorithm, can be written as the cosine of theta, sine of theta, multiplied by square root of 2 times a exponential 1. And now you can probably see that we can tie all these things together, because we can also write this as, we know that cosine theta, sine theta, we know that this can be written as u1, u2 divided by r. We originally wrote that this pair was equal to r times this pair, so we can just drag r over to this side. And we just proved that this factor has the same distribution as square root 2 multiplied by minus the logarithm of our r squared. That's what we just did up here, because r squared was uniformly distributed. And now you can probably see where our algorithm comes from, because we can just put this r inside this over here. So this is u1, u2, multiplied by some factor over here, 2 times minus the logarithm of r squared divided by r squared. Since we only want to simulate one of these, we only take the first coordinate. So x1 has the same distribution as the first coordinate up here, u1 times square root 2 minus logarithm r squared divided by r squared. And this was what we wanted to prove. Now I'm going to open up my PyCharm, and then I will show you that this actually works in practice, because it can be a bit hard to see why this works just using this theory. Yeah, so I'll see you when I open my PyCharm. Okay, welcome to my PyCharm. Now I will build up my code using some copying and pasting, since I don't want to waste time writing everything out. So first of all, I import some packages. I import the NumPy package, the NumPy random. The NumPy package gives me some tools like square roots and some important methods of storing data. And then the random module lets me simulate my uniform random variables, and then the rest are used for the plots. So my simulations, well, I will need to simulate my u1, my u2, and then I have to calculate my r squared and see whether or not this is less than or equal to 1. So I built, well, this is the function I used to make my output, where I take u1 and I take my r squared, then I return u1 multiplied by the square root of minus 2 times the logarithm of r squared divided by r squared. This is exactly what we just showed it had to be. And then finally I build some plots. And I have to be a bit careful now, because I actually have to build a function called sim, which simulates my x's, and it takes an n, which is the amount of simulations I want. So for I in range up to n, I then I could set r as q equal to 2, for example, something which is larger than 1, while r as q is larger than 1. I then simulate u1, I simulate u2, and I define r squared. This will keep happening until r squared is larger or is less than 1, then it stops, and then I define this function. I will need an output, which I will need up here. Output equal to numpy zeros. I will need n of these. And this function, let me just put it all the way outside. So at this point, I have sampled u1 and u2 until they are within the unit circle. So now I build my x, which is then equal to f of u1 and r is q, where f was this function up here. And then I append my x to my output. Then finally I return my output. Okay. Then down here I simulate 10,000 realizations of this, and this should then be standard normal. I then create a plot where I overlay with the curve of a normal PDF. So if I run this, this is the plot I get. If I just try to make a bit more bins, whoops, not what I wanted. If I make 100 bins instead, maybe this will be a bit prettier. We can see that there are, overall it fits quite well. Let me put some more. This should go fast enough. So you can see that this curve fits very, very well with our distributions, or with our observations. And you could then transform this x such that it had another normal distribution instead of just the standard normal distribution, but I will not do this. I did that in my Box-Muller video, so you can see it there if you're interested in that. Thank you very much for watching this video. If you found it interesting, you could consider checking out my RNG playlist, which goes through a lot of different methods of generating random variables. Especially the video prior to this one, the Box-Muller algorithm, should be interesting to you if you also found this video interesting. If you have any ideas for new content or any questions, please post them in the comments down below. I would very much like to improve on my video making, so if you have any ideas as to how I could do that, or just ideas for very interesting topics within probability theory or statistics or Monte Carlo simulations, please just let me know. I really do welcome your feedback. So yeah, I guess there's not much else to say except please have a nice day, and I hope to have you as a viewer on one of my future videos.